Good morning, students. Today we will see the relationship between Fourier series and linear time invariant systems. More specifically, we will see if we have a periodic signal x of t, an input to a system, how do we calculate the output yt without doing convolution? Before that, let us study what is the frequency response of a system. Okay, as you know, if I have an input x of t, the output y of t is x of t convolved with h of t. Y of t is equal to, from minus infinity to infinity, h tau x t minus tau d tau, which is h tau e to the power of x if I have exponential input e to the power of st, where s is a complex number, then t is changed to t minus tau. Then we have e to the power of st, which is independent of tau, and we have from minus infinity to infinity h tau e raised to minus s tau d tau, which is, we call this h of s. Therefore, the output yt is h of s times e raised to st. H of s, we call it the transfer function of the system, which we will study in chapter 5. And it is called the eigenvalue. And e to the power of st is the input, which is the eigenfunction. So the output is simply the eigenvalue h of s multiplied by the eigenfunction e to the power of st. Now, s is a complex number, so it can have real part and imaginary part. In this chapter, for the case of Fourier series, the real part is 0, and when s becomes j omega, it will become purely imaginary. So h of s at s is equal to j omega, it will become h of j omega. From minus infinity to infinity, h of t e to the power of j omega t dt. So if you see this integral function, it is a function of omega. We call this the frequency response of the system. What is the frequency of the response of the system? In short, the frequency response of the system is the characteristics of the system in frequency domain. We can study a system, which is the impulse response h of t, in time domain, and also we can look the same system in frequency domain. And the frequency response of the system is called the behavior of the system. It shows the behavior of the system in frequency domain, and it is given by Fourier transform of h of t, which is from minus infinity to infinity h of t e raised to j omega t dt. Now, if I have a periodic signal input to my system, which is represented by from k minus infinity to infinity a k e raised to jk omega naught t, where omega naught, as you know, omega naught is 2 pi divided by the fundamental period t. Now this is an input to my system, which is a periodic signal. Then the output is from k minus infinity to infinity h jk omega naught ak e raised to jk omega naught t. So what happened? What happened is each frequency input ak is multiplied by the frequency response h at that frequency k omega naught. And when it comes out, ak becomes h at k omega naught multiplied by ak, which means ak, it can go through depending on h, the frequency response at k omega naught. For example, if the frequency response at k omega naught is equal to 0, then at the output we will have 0. So that means a cannot go through the system. So the system acts like a filter, that means. So h jk omega naught can be written as in polar form with magnitude of h jk omega naught and phase e to the power of j at an angle angle of HJK omega naught, which is magnitude phase representation. The Fourier series coefficients for the input are AK. The Fourier series coefficients for the output are BK. BK is equal to HJK omega naught times AK. So AK times HJK omega naught are the set of Fourier series coefficients for YT. So the output YT is without convolution. We just do this summation. What we need to find the AKs for the input, okay? And then we need to find the frequency response, H, and evaluate at each K omega naught, and we should find BK is equal to AK times HJK omega naught. And we do the summation. That's all to get the output. Let's see this example. In this example, we have x of t 1 plus half cos 2 pi t, cos 4 pi t, and 2 over 3 cos 6 pi t. And I have a system h of t e to the power of minus t times ut. This is exponentially decaying function and it starts at t equal to 0 because of ut. Now using Euler formula, as you know, we can write this cosine in terms of exponential function, which is e raised to j2 pi t plus e raised to minus j2 pi t divided by 2. Then we can find the AKs for this signal, which is a periodic signal input. A0 is 1, A1, A minus 1 is equal to 1 over 4, A2, A minus 2, 1 over 2. A2 is the second frequency, the second harmonic. A3, we have the third harmonic also, A3, A minus 1 over 3. Then we found the AKs. Then the output is summation from k minus infinity to infinity. In this case, from minus 3 to 3, because we have only from minus 3 to 3, HJK omega naught e raised to JK omega naught t. So we need to get the B case, okay? Before we get the B case, we need to find the frequency response, so of h of t. The frequency response is hj omega from minus infinity to infinity h of t e raised to j omega t dt. So we integrate from 0 to infinity. We add the exponents here, and then the integration of this will be from infinity to 0, 1 over 1 plus j omega. Now we need to evaluate at omega 0 to get the DC part hj0 at the first frequency omega naught. Omega naught in this case is 2 pi, at 2 times omega naught, which is 4 pi, at 3 times omega naught, which is 6 pi. You see, this is what I did here. I found B1 at omega naught. B1 is A1, 1 plus 1 over j omega naught. A1 is 1 over 4 and 1 over 1 plus j2 pi. B2, A2 times 1 over 1 plus j2 omega naught. 2 omega naught is j4 pi, and so on. B0, the DC part, is when omega 0, then it will be h at 0 is 1, so a0 is 1, so b0 times a0 times h at 0 is 1, which is b0. Then we do this summation. After that is simplification. So we see here we add this summation, and then we can simplify these to cosine. We can group these two and write it in terms of cosine, and we can take b2 and b minus 2 and we can write it into cosine again. We can take b3 and b minus 3. We can write it in terms of cosine. This is how to calculate the output by t. Here also you have other example. Here the same thing as I explained, to calculate first find the AKs, then frequency response, then we do the summation. Here I have a more simpler example, which is x of t 1 plus half cos 2 pi t and h of t given by this. So for this we have a0 1, a1 1 over 4, a minus 1 1 over 4, and we calculate hj omega like before. It is the same, and we do the summation In this case, we have only B1, B minus 1, and B0. And then we do the summation like before. Now, what is happening? Here, if the input is A0, the output is B0. B0 is A0 times H at 0, at frequency 0. B1 is A1. If the input is A1, the output B1 is A1 times Hj at omega naught. What does it mean? For example, if the frequency at omega naught, if the frequency response is 0, then Hj omega naught is 0. That means B1 is 0. Even though we have an input A1, we do not have B1. That means that particular frequency, the input signal at that particular frequency cannot go through the system. That means same, for example, if H at 0, if the frequency response at 0 is 0, then even though we have A0, we will not have B0. That means it will not pass through the system. That means the system acts like a filter. So the impulse response of a system is simply a filter. And we come to the concept of filtering. So what is filtering means? Filtering means changing the relative amplitude of the input signal or eliminating the frequency component of a signal when it comes out of the system. Okay, the frequency components of the output depend on the frequency components of the input and the system frequency response. We have two kinds of filters, frequency shaping filters and frequency selective filters. The frequency shaping filters change the shape of the input spectrum. So that means we have for each input frequency, we'll have output frequency, but with different gain, with different amplitude. So the amplitude of the input frequency may be changed. It can, when it comes out of the system, it comes with a different amplitude or which gives different shape. Frequency selective filters only pass a certain frequency components undistorted, and it eliminates a certain frequency component. It passes certain frequency without distortion or without attenuation, and it eliminates other frequencies. This is frequency selective filter. Where do we find filters? We find them in many electronics devices and communication devices. For example, radios. Radio, when you are listening to a certain channel in radio, then you are tuning. So when you are tuning, what you are doing is you are selecting a certain frequency. That means you are changing the filter, you are adjusting the filter to select a particular frequency. The same in TVs, television. When we are listening a certain channel, we are listening at a certain particular frequency. So which component will do this? The filter. The filter selects a certain particular channel, and we can be able to listen in the radios or watch in the television. We have continuous time filters and discrete time filters. Okay, for continuous time signals, we have continuous time filters. For discrete time signals, we have discrete time filters. For discrete time filters, which we will study in 320, they are periodic with 2 pi. And the low frequencies are around 0 and around 2 pi. And the high frequencies are around pi, 3 pi, and so on. This is, for example, low frequency. And this is high frequency. High frequency means it rejects low frequency, it passes high frequency. And this is band pass filter. It selects a certain band of frequencies which are not low or which are not high, but in between. Ideal frequency selective filters. An ideal frequency selective filter is a filter that completely rejects certain frequency components and passes without attenuation certain frequency components. A filter that exactly passes complex exponential signals at one set of frequency without any distortion and completely rejects signals at all other frequencies. For example, here you see a low pass, an ideal low pass filter. After omega c, it will pass between minus omega c and omega c. Omega c is called the cutoff frequency, and it will reject frequencies above omega c. This is high pass filter. It rejects the low frequencies and it passes high frequencies above omega c. And here is an ideal band pass filter which selects between two cutoff frequencies, omega c1 and omega c2, and eliminates low frequencies and high frequencies. Simple RC low pass filter. A simple RC low pass filter is a filter where we have the resistor here and the capacitor. Here is the voltage source. That means if I have an input here, then the output voltage here, if we relate the output voltage with the input voltage, the relationship, and if we find the system response for this, considering the capacitor voltage is the input and Vs is considering the capacitor voltage is the output and Vs is the input, we'll find a low pass filter. For example, let the input voltage is e to the power of j omega t. Then this is first order differential equation. The differential equation relating the input and the output is given by RC, the derivative of the capacitor voltage dVc by dt plus Vct is equal to Vs of t. Vc, the capacitor voltage, is equal to e raised to j omega t, which is the eigenfunction, times h j omega, which is the frequency response. So if we substitute here for Vc of t, this one, what is the derivative of Vc of t? The derivative will become j omega times h j omega e raised to j omega t, and plus Vc of t is this one, and then we have is equal to the input. The input is e to the power of j omega t, and if we rearrange this, we have h j omega is 1 over 1 plus RC times j omega, which is a low pass filter, the frequency response of a simple RC low pass filter. In the next lecture, we will discuss more this RC low pass filter. But let's see the impulse response of this system. What is the impulse response of the system? That means considering Vs the input and Vc the capacitor voltage the output, the impulse response is given by 1 over RC e to the power minus t over RC. Okay, how we find the impulse response? From the step response. By differentiating the unit step response, we can find the impulse response. How we find the step response? We give to the circuit a unit step input and we'll find the capacitor voltage for unit step input. The capacitor voltage having the homogeneous solution and the particular solution that we studied in chapter 2. Then the complete solution for a unit step input will become this. This is a good exercise. You can try it at home. So give a unit step input, find the homogeneous solution, find the particular solution, and consider an initial condition of 0 for the capacitor voltage. You will find the step response given by this. And if we differentiate this, we will find the impulse response given by this. If we plot the impulse response, as you see, it is exponentially decaying function, and the step response exponentially growing function. Okay, so in the limit when t goes to infinity, the step response reach to 1, okay, from the previous equation. When t goes to infinity, e to the power of minus infinity, which is 0, 1 minus 0 is 1, then the output will become 1, okay, which gives this graph as a function of time. At t is equal to tau, then we have at this time constant, the capacitor will be charged to 1 minus 1 over E as this value. And tau is equal to RC is called the time constant. And h of t, the impulse response, is given by this graph as a function of time when you see it as a function of time. So in summary, in this chapter, we studied Fourier series representation of periodic signals. That means how we find the AKs. First of all, Fourier series changing from time domain to frequency domain. For what kind of signals? Periodic signals. And how we calculate the AKs. The AKs can be calculated as AK is equal to 1 over t, the integration of x of t e to the power of minus jk omega naught t dt. And we studied the relation between Fourier series and linear time invariant systems. We studied about frequency response of systems. I hope you understand this lecture. If you have any questions and doubts, you can always write me an email. Thank you very much for listening.